Hi guys, welcome to another series of videos. We haven't quite finished the previous series, make sure we're recording, we are. But I thought I'd start another one because we are almost there really. It's just the nightly that we still have outstanding, and let's have a quick look. If I come here, as you can see, the nightly is already kind of running. I mean, we're not running the full set of tests and they are not all passing. But we're almost there, so I think it's time to move on to the next challenge, and then I'll probably over the weekend finish that series of videos. The next challenge is, well, we have completed the writing of the thesis. You can see here the sort of the combined volume with everything on it. It contains both the thesis as well as all the supporting material. The actual thesis is a lot smaller. That I shall be presenting. That is the actual thesis, so a lot smaller. But since my Viva, which is the final meeting you have to present your thesis, is coming up in about a month or so, I thought I'd get ready for the Viva by doing a series of lectures on Dogen, really, on what Dogen's about, how it came to be, and it's sort of an introduction that takes us from the very beginning of the ideas to the current state. And that's a great way to revive all the knowledge that we accumulated over 7 years, because there's a lot of things I haven't touched in a long time, which is really not fresh in my mind anymore. I mean, I read a lot of papers. In fact, I can't quite reach them, but there were several hundred papers that I read, probably about 120 papers or so. Um, some more important than others, but I won't be able to recap all of those papers. But what I'll do instead is focus on the core ideas and how they are quite logically connected to each other, because they're a sequence of steps of traveling across this terrain. So the first lecture we're going to do is just going to be sort of a quick introduction. I've delivered this before in our computational neuroscience lab, which is where I did my thesis or my PhD. It was done for a non-programming audience, so I suspect some of these themes here are not treated in the level of detail required. But what we'll do is in the subsequent lectures I am going to go through the notes. So I've created a separate volume. This was a bit too big to go on the thesis itself. As you can see, I mean, this is just not suitable as a thesis. It's just too much stuff. So what I did is I took out all of the preamble, all of the basic knowledge into a separate paper, and this paper is referenced on our website, so you can get a link there. I'll also put that on the description of the talk, and you can access that paper right now. The thesis you can't, but this paper you can. And what the paper does is it basically shows, or it's a compendium of the knowledge that I gained while trying to understand what model-driven engineering is. It's also a bit of a critique as well. So the first lecture is going to be sort of an overview of model-driven engineering, and why one would want to do that and what problems there are. But it's sort of a high-level thing, as I said, because it was designed mainly for non-computer scientists. Then what we'll do is we will go through the notes chapter by chapter, and this will be a bit more detailed and more suitable for computer scientists and software engineers. Once we've done all of this, I think it'll probably be about one video per chapter maybe. Once we've done all of that, then I'll get into MASD. Now I can't actually use my thesis, I don't think, because it has not been published yet, so I don't think it's a good idea to use material from the thesis. So instead what we'll do is we'll just do a presentation that takes the core ideas of the thesis, and then sort of provides an overview of them. Hopefully after the Viva, if everything goes okay, I will continue or finish up the series of lectures with the contents of the thesis. Maybe that'll be a good idea, but we'll see how it goes. This is all very experimental. The main purpose of this really is to prepare for the Viva, so we will modify things as we go along. The other slight change to the usual way of doing things is, as this is also sort of an outreach exercise, Dogen is now readying itself for external contributors, if there's any out there interested. And so I thought this is sort of, as usual, a two-in-one kind of, or three-in-one even kind of exercise. I think it's very difficult for you to get the gist of what Dogen is trying to do just by looking at the source code. And so hopefully this series of videos will give you all the background you need to understand the core ideas of what we're doing. It's not that what we're doing is really complicated, it's just that it's very different from how things are done normally. And so if you don't come from a model-driven engineering background, you're probably going to find a lot of the structure of the code very puzzling. However, it tends or tries to use a lot of core concepts of model-driven engineering, so hopefully it should make sense once you've gone through these lectures. And the final note, I guess, is that we're going to try to stick to our roughly 1 hour sort of content, probably a little bit less, we should see how it goes. The idea being that we don't want each lecture to be too big. It should be something you can watch while you're doing something else, or you know, with a bit of focus, but not something that's too intense on the brain. So hopefully that's by making it an hour, it should be sufficient for that purpose. And if you got any questions or any comments, since this is an outreach exercise, just leave a comment on YouTube. I'll post this on my Twitter feed in case anyone is interested. We didn't really have any externals trying to contribute to model-driven engineering, but like I say, now that I'm almost done with the PhD, I will start the outreach work, which will mean I will probably make things visible in places like Twitter and Reddit and so on, to see if anyone is interested. So this the questions on YouTube may be more relevant now than they were in the past. Okay, so that's the preamble. So without any further ado, let's get on with it. I think my org mode present is a bit deficient. Let's hide the cursor, it just makes life a little bit easier. Right, so what we'll do first is we'll provide some historical context of how model-driven engineering came to be. Now, I'm not going to say that this is actually how history developed, because I think, as always, history is always rewritten by the people that get to write history. So I am rewriting history here. This is not really necessarily exactly how things went on the timeline, but if you were to look at the general ideas in terms of the history of software, you can kind of get this view of the world. So as you say here, there are two big problems that we all had to deal with in terms of programming and large scale. As soon as you start coding, and as soon as you start coding for significantly large projects, you end up with a lot of expenditure to do with the development and maintenance of systems. And the more you can automate the development and the maintenance of those systems, the more you can save. So automation and cost savings are they're connected really. And what you really want is, you want as much as possible to get the machines to do the work that they can do, so that humans don't have to do that work. And that's kind of a fairly if you look throughout the history of computer sort of science and then eventually software engineering, that's what kind of happened really. We started off with very large machines that required people with extremely specialized knowledge. They mainly physicists and electrical engineers and people with low-level hardware knowledge in order to build the first computers. And eventually the notion of software was extracted out of the notion of hardware. We started to have some kind of basic machine code that it wasn't very obvious in the 40s and the 50s that such a separation would exist, but eventually as machines became more advanced, it became obvious that machine code was separate from the hardware. And that happens because instead of using, say, plug boards where you are rewiring the plug boards, you want to create a soft notion of that rewiring. And that's how machine code kind of fills in that gap. You start to reprogram the machine in a software way rather than a physical way. And once you got to that notion, the next logical step was to think of things like assembler. Assembler was a way to say, well, instead of dealing with these numbers, I mean, we're talking about reams and reams of numbers, the neocortex is not really designed to deal with reams and reams of numbers. So it kind of makes sense to try to get closer to the way the neocortex works, which is words and sentences and so on. So then you start to see the first efforts in that sort of direction with the creation of assembler. And assembler was still a very low-level language, but if you compare assembler to machine code, for those of us that are old enough that programmed in machine code is literally just a set of hexadecimal numbers. I mean, if you were to really go back to the beginning, machine code was literally just binary, and that was it was normal for people to program in binary. Um, and once somebody figured out that actually you can do a representation of binary in hexadecimal, that life became a bit easier because, as you can imagine, programs become much more condensed. So by the time I joined programming, although I've missed all of this in terms of the historical timeline, it was very common for us in Portugal in the 80s to get magazines with code in it. And they used to do dumps of the code in machine code. We had these masses of listings in machine code in hexadecimal that you just type into the computer, and you could make heads or tails of what you're typing, and you just type for days on end, huge listings of machine code. And in the end, if you were lucky and if you didn't make any mistakes, I don't know, say 20 pages or 15 or 10 pages of machine code, you type all this in, and eventually you'd run, and you'd get a game out of it. And it was fairly common in the 80s to do this. Of course, this was not common in terms of the programming history timeline, because by then we had moved on from machine code to assembler, from assembler to high-level languages. But some of us still got to experience what it meant to deal with machine code. So you can see, we can imagine this as sort of a progression of abstraction, where you start off with machine code, you move to assembler. At some point somebody has the idea that assembler actually is still not high level enough, so you want to create the notion of high level language, and then that's where languages like Fortran and Lisp and so many others came. They are English descriptions, I guess you'd say, from a computer science perspective, of what assembler should do. And the compiler then becomes the tool that converts this high-level description into a low-level description, and then eventually you reach machine code, and machine code executes. So the idea here is to automate the process of development, so that anything that a machine can do, the machine does, and anything that only a human can do, well, that's actually put aside for the humans. This is a very important notion. We normally tend to look at it in terms of abstraction. We tend to think of the idea that we keep on abstracting away things to the point where we are almost at the same level as the normal discourse of humans. But you can also see it from this flip side, which is we're trying to automate as much as possible because humans are expensive. So we're trying to distinguish between tasks where humans add value versus tasks where humans actually have a detrimental value. Because as anyone that was experienced in programming or in machine code or assembler knows, it is actually really difficult to do this. And that's because the neocortex is not designed to do to deal with very large numbers of numbers, very large listings of numbers, and we make mistakes. That's not really what the architecture of the neocortex is designed to do. So once you go through this kind of sort of timeline and this kind of notion of continual abstraction, the next thing the next logical step in that is once you've created a lot of software, even in these high-level languages, you start to think that perhaps this road of abstraction is not complete. Perhaps one can still go one step further and extract some kind of essence of a system, which we may call now legacy, and transport that that essence over to non-legacy platforms. So by that we mean, imagine you created a very large system in COBOL. There is some kind of knowledge that's encoded in the COBOL sort of code base, and there is a potential, at least hypothetically, there's a potential for you to extract that domain essence and take that and move it to a newer platform, say for example .NET. And I don't really mean just create a code transformer that just takes away a bit of COBOL code and converts that into something else. What I mean is more like extracting the higher level patterns. And so with that, we move over to this second slide. Um, what people that thought quite deeply about this concluded was that there's actually two kinds of models, and we will discuss in more detail what we mean by a model. But if you think of a system is sort of conceptually divided in two parts of the system. There are parts that are independent of the platform, and as we shall see in this series of lectures, words like platform, model, and platform independence and so on are quite loaded words, so we're going to have to spend a lot of time describing what we mean by those words. But just using a generic software engineering notion of a platform, you can imagine when you do code, part of the code that you do is very strongly bound to the platform. So if you're doing some, say, .NET code, we're talking about the .NET libraries, we're talking about the operating system in which you're going to run that code. We're talking about lots of things that are very specific to the platform you're going to deploy and run in. But there's also a set of concepts that are completely agnostic of those platforms. Normally, we tend to think of those concepts as the domain. So if I talk about finance, or if I talk about computational neuroscience, or if I talk about any of these domains, I don't particularly care if you're going to run this in C# or C++. Maybe there's some requirements in terms of speed or in terms of performance and so on, which may force you to choose a certain set of platforms, platform options, right? But if you abstract yourself from that for a second, those very high-level constructs, they are not platform specific. So the person that works on computational X, and X could be finance or could be computational science or whatever it is, that person doesn't really care about implementation level details. The trouble, and this is what in the 2000s people kind of concluded, the trouble was that we bundled the platform independent concepts with the platform specific concepts, and as such it was very difficult to extract these two things when you look at a system. And I guess we can all relate to that, because if we were to look at any program, any code base that we work on at the moment, and we're talking about 2022, so it's a long time since these ideas were discussed, we still would find extremely difficult to separate the domain from the platform specific stuff. This never really, this idea of separation, I mean, conceptually, of course, we all try our best. We all end up with architectures where we have the domain types in a separate assembly, or so conceptually we do try that, but in practice, the dream that you would be able to take a platform independent model and simply retarget that model on another platform, that never really took off. And the reason why is because we still haven't managed to work out how to do this separation in a way that is suitable for transformations. So I'm already introducing a lot of concepts that are really model-driven engineering. It's very difficult for somebody who's been stuck in this land for a long time not to do so, but we will try our best to explain these things. So I've used the word model quite a lot, and so I would like you to understand that model is a word that we as software engineers, we use this all the time. In fact, pretty much anyone that's in any scientific endeavor uses the word model. We don't really mean model in the sense of the loose sense of the word. If you really want to learn about models and modeling in this kind of more mathematical and sort of how should I put this, in this notion of model versus theory and so on, I highly recommend you read Derman. I think this book is really, really good. This gives you a really layperson's understanding of models and theories, and it explains what it is that you're trying to do when you're using the word model. So for example, one of the things Derman talks about is when you create a plane, a model plane, it looks very much like a real plane, and you can probably use that plane for a lot of things. You could use that in I don't know, in a tunnel to test aerodynamics and so on. But we don't confuse that plane with the real plane. There's the actual plane, and there is the model of the plane. This is what we normally mean when we use the word model. And the idea of a model is that model is always not the real thing. It's something that's less complex, less It extracts a subset of the properties of the real thing, and it enables you to deal with it as if it was the real thing. And you can reach a lot of conclusions with the model, but you can't confuse the model with the real thing. This is the important thing. However, once you enter the world of MDE, it's not sufficient, or model-driven engineering, it's not sufficient to just have this general notion of a model. And a very important point here as well is that we're not searching a theoretical definition of a model. We're not looking for something that's going to be theoretically complete. We're looking more for an engineering definition of a model. We need something that can be used to create systems right now. So what exactly do we mean by a model? Actually, to be honest, I'm kind of rephrasing myself here, because as I said, the informal definition of model, which is what we discussed so far, is the partial representation of reality. And the objective of creating that partial representation is to accomplish a certain task, like for example studying the impacts of the wind in a play. And your model is not to be confused with reality. This is very important. But then we enter the more technical definition of a model. So what do we mean by model in model-driven engineering? So a model is a graph-based structure representing some aspects of a given system and conforming to a definition of another graph called a meta-model. So a model is said to represent a system. And Volter said that a model is an abstract representation of system structure. So here we already are trying to make a conscious effort to say, can we separate certain aspects of a system into another construct called the model? So as I said before, when I was talking about PSMs and PIMs, we don't really do that normally in software development. Whilst we say that we try to separate, say, the domain concepts from non-domain or platform concepts, we don't really have an explicit way to define that. What you end up with is a set of assemblies that are understood to mean platform specific or platform independent. So a team, by natural language, reaches an agreement of where they should place certain types or what technologies you're allowed to use in certain assemblies to keep those assemblies clean from platform concepts. But there is no official or no formal representation of that concept. What we're looking for in model-driven engineering is to formalize that. So we as much as we may think that we don't really normally deal with models are always there. It's a very pervasive concept, because as soon as you start programming, you start creating models. And those models could be, the most obvious things in programming, we always think about diagrams. We always think of a diagram as a model. But actually that's sort of misleading. A class is a model. Pretty much everything you do is modeling, right? Your activity, your entire programming activity is a modeling activity. It's just that we don't think about it explicitly. And that's the important thing. We don't tend to separate the modeling activity from the programming activity, because we think that programming and modeling are just one thing. What the model-driven engineering camp try to do is they try to say, well, what if we were to separate the models from programming? What if we were to create a modeling language that is like a programming language, but designed for modeling? And of course, as soon as you think of a programming language, you think of semantics, you think of compilers, and you think of rule-based sort of structure. And that's kind of what we're trying to achieve here. We are trying to create a language which is a domain-specific language that is designed specifically for modeling. I don't think my org mode is displaying images here. Let's see if we can. Okay, sorry, I don't think we can see this picture, but the idea, I think maybe we can just, if I just exit for a second org present. Let's just quit org present. I think I have an image directory here. And if I just open up Northwind, we should be able to see the image. So here is an example of a model as we understand it from computer science stroke software engineering perspective. This is a very old model that we used in Dia many versions ago. So everyone is probably familiar with UML, even though we don't use it very much these days as it was before. But you as soon as you see this diagram, you can in your head you start to visualize a code structure. You start to see a set of classes with certain attributes. You start to see relationships between classes. You start to see all sorts of structure that is very meaningful to a programmer. Um, and it's not obvious because we lost a little bit the knowledge that we used to have with UML. We lost all of the formality that used to come with UML. In the past, UML was designed to be a tool, part of a stack, as we shall see in the future. And the idea would be that you would model with UML, but you would also develop code. You'd use UML as the starting point for a pipeline of codes, and it would eventually generate the code for this model. Um, that vision never really kind of panned out as a whole. I mean, of course, there's people that are doing that, but it never really kind of became full-fledged. But that was kind of the idea. And if we just go back to our org present big, I believe. So whilst most of us look at UML as some informal diagramming tool, in reality, UML has the power to become a formal diagramming tool with providing a representation that's suitable for transformations. So just to recap then, so modeling is the process of creating models for a system. But the models are not just pretty pictures as we do with UML these days. So for example, if you use plant UML, as we do quite a lot, these are just pretty pictures really, some kind of way of representing the system. The idea that came with modeling in the MD context is not just the pretty pictures side of it, but to actually create formal pictures. Well, actually, pictures is already sort of implied, but formal the representations, like codes, but at a higher level of abstraction. And the idea would be then that the models are expected to contain enough knowledge to create some aspects of the system, um, for example, via code generation, and transforming the formal representation of the model into code. That's the vision that people had. And you can see why they wanted to do this, because if there was a way to formally represent the platform independent code, and even the platform specific code, one could then say, actually, can you please target, instead of COBOL, can you please target .NET? Or instead of whatever technology you were stuck with in legacy, can you please target something else? And so now this takes us to the sort of the broad definition of model-driven engineering. So the idea with model-driven engineering was to create a development paradigm that uses models as the primary artifact of the development process. And ideally, the implementation would be semi or fully automatically generated by the models. And the idea with MD is to go beyond the pure development activities and to imagine the complete software engineering process as being model-driven. So if you remember, there was in the past there was this notion of driven technologies. I mean, we all went through test-driven. After object-oriented, I think everything became driven, test-driven, domain-driven, model-driven, and so on. What they were trying to use, trying to represent or symbolize with the word driven, was that they didn't want the software development process to be a mismatch of approaches. They wanted one approach to be the approach that orchestrated all other things that are needed in a software engineering sort of environment. Clearly, none of these driven approaches won, and if we look at it from our hindsight in 2022, we could say that actually there are so many things that drive software engineering that there's never going to be a driven methodology that's going to orchestrate everything. But each of these approaches can be combined together to form a broader approach to software engineering. And so these days, I think everyone would accept that their coding is model-driven, it's probably test-driven, and it's certainly domain-driven. Sorry, I said model-driven there, but I made a mistake. I didn't mean model-driven. I mean that it was domain-driven, was test-driven, and many other things, object-oriented, and so on. So all of these things are now aspects of the way we develop. The only one odd one out was that we never really incorporated model-driven techniques into the development process. We incorporated all these other approaches, and they didn't really become the driving force of the development process like the creators had envisioned, but they all became a component of the toolbox of all the developers, with the very glaring exception of model-driven. So what is the proposal? What are the model-driven people trying to do then? They try to basically say, just like Wirth had said, that software engineering is basically it's fundamentally two things together. Is the creation of algorithms and the creation of data structures, and that's how we come up with programs. This is it may not appear like a very insightful idea to us now, because we are sort of the children of Wirth, and we're the children of Dijkstra and all these other people that came before us, and von Neumann. So we don't really think too much about it. I mean, we don't think about the von Neumann architecture anymore. We don't think of how intelligent and how clever it was to separate code from data, and then to do the opposite, to start to say that code and data are the same thing, as McCarthy did with Lisp. Those really fundamental ideas are all part of what we now call common knowledge. So we don't really spend a lot of time thinking about them. But actually, what Dijkstra said here, what Wirth said here, is actually really fundamental. When we do programming, we do two sets of activities. We do the modeling of the data structures, and we create a set of functions or algorithms that operate on those data structures. And that's really what we call programs. Now this equation has been rearranged many times, for example with object orientation, where we started to say that actually an object is equal to algorithms plus data structures. So we started to say that the behavior of the object was the algorithms, and the state of the object was the data structures. We sort of created lots and lots of different takes on this fundamental equation that Wirth came up with. But the core nature of it has not changed. The MD people started to try to change this notion. They tried to say, actually, if you were to take a higher level approach to Wirth, that would then mean that we have two sets of concepts. There are models and there are transformations. To be precise, really, this I should have written this the other way around. There should be transformations plus models. I just respected the way that these two equations were written, but transformations correspond to algorithms and models correspond to data structures. What they're trying to say is that if you were to go one level up from where we stand, all of this is encapsulation. All these notions are encapsulated into models, and if we were to transform models, we can attain software. So as an example, imagine a pipeline whereby you start off with a model representation in UML, and then through a set of transformations you convert that UML representation over to, say, C++ or C#. That's kind of what they're envisioning here. They're trying to conceive a world where a pipeline takes a set of models from one sort of representation to another, and eventually to the final representation, which is the execution in the machine. And then, of course, if you're a model-driven engineering person, you don't stop there. You would always continue abstracting, and this is a very confusing thing to do. It took me quite a while to understand the way of thinking in model-driven engineering. Model-driven engineering, in a way, is a bit like maths. You keep on creating abstractions on top of abstractions on top of abstractions, and you don't seem to ever stop. So it seems pretty abstract, this concept here, but they were not happy enough with that, and then they state that the logical conclusion is that actually transformations are models. That's something that's very complicated and very difficult to understand. So what we'll do is we will wait for our chapter 2 and discuss that when we get there. But just the general idea that they're trying to say is that everything is a model. Even the way we transform models is also a model. So now that we've kind of did sort of an overview of what it is that we're trying to achieve, and we still are half an hour into our talk, we will now proceed to get a little bit more into the detail. So there are two types of models, really, if you think about it. There is a model that you use to express things, so for example UML, but there's also the notion that UML is described or specified according to a language, which you call a DSL. Conceptually, that language could also be represented by a model. I mean, nothing stops you from creating a set of classes that represent the concepts that you need in the DSL. After all, a DSL is just a language, right? And the language could be described as a set of concepts. And you could even think that programs, in a way, are also a language, really, because we create a set of terms that become our vocabulary, which is what model-driven engineering defends. So there's nothing stopping us from creating a model for a model. And in fact, that's exactly what model-driven engineering people did. I mean, there were people before them. This history of meta-models is a very interesting one. And if you were to read my notes, you would see interesting notes on how that came to be. We'll discuss that when we get to the PDFs. But as I say, this is a revisionary history of software. I'm giving a lot of credit to a lot of ideas to model-driven engineering as if this was a unified field, but in reality, model-driven engineering is a step on the road of a very long road that comes all the way from the beginning of programming. And model-driven engineering is more like the point at which we are taking all these ideas and disparate ideas really and trying to combine them together to create a field. So a meta model is the formalization of this idea that you can use a model to define a model, and the meta model is that model that is used as the base. We don't really talk about meta models very much in programming, but actually they are really fundamental to the work that we do. The reason why we don't think about them so much, particularly if you don't come from a small talk or from a list background, is because we tend to treat the meta model as our starting point. Not many of us spend time thinking on what's a class, unless you do a bit of reflection, I guess. But even then, you can't introduce a new concept of a class-like thing into, say, C# or C++. Those things are given. And because of that, most of us start off by not realizing that there is such a thing as a meta model. If you were a Smalltalk developer or Lisp developer, you'd have this quite ingrained, particularly because these languages treat reflection as a first-class citizen, especially Smalltalk, really. The meta model from a programming perspective is the class, function, all these things that we use quite freely without thinking about. And mainly that is because you can't really interact that freely with these concepts. You normally tend to interact with them in a very strict, controlled way, such as, for example, using reflection. But if one were to think about this in a more abstract way, you can imagine that somebody had to define the notion of a class. There had to be a class called class. There had to be a class called function. And if you were to think of a compiler, the compiler would read a text file. Imagine you're designing a compiler from this perspective of meta modeling. You would have to have a model of the language in the compiler. And that model would have to have, like I say, a class called class, a function called function, and so on. And you can think of a program as a serialization of the meta model of a programming language. And you can imagine that the compiler is deserializing this program into memory, and validating that the syntactical and the semantic, as much as they can validate semantics, the semantical constructs are valid according to the definition of the language. Once you start down this road, then you start to think of UML also as something that must require a meta model. So in other words, if you think of UML not just as a graphical language to design informal diagrams, but if you think of it as a formal language to design diagrams, then surely there must be a definition of what a class means or what an association means, such that you can then take a UML diagram and say, this is a valid diagram. Now, the reason why you must be able to do that is because when you're code generating, you must make sure you're generating valid code. So the only way to ensure that your UML diagram will generate valid code is by doing, just like what the compiler does, you need to do some kind of check to ensure that the, the diagram it does not contain any nonsensical constructs. And that for that you require exactly like a compiler requires a formal specification. What do you mean by a class, and what do you mean by an association, and so on. And so UML also has a meta model. XML documents have got XML schemas. And in XML itself actually will be a very interesting topic of conversation, but we will get a bit lost here because of course there is the schema of a schema, and there is the schemas that you normally define. So you can imagine that this process goes upwards, as you shall see. Relational databases also have a meta model, so you have tables and columns and so on. And of course you can imagine that somebody had to define a table, well, a class for a table or a construct of a table. And because this was for a neuroscience audience, I spoke a little bit about NeurML, which is a XML-based specification that enables you to talk about neurons. But we're not going to spend too much time on that, just to avoid getting lost. So, as I said, why would you bother defining a meta model explicitly? So, I mean, you, as a computer scientist or software engineer, you say, well, I've been creating compilers for, I don't know, ever since we moved away from machine code. Why do we bother with now coming up with this meta model idea? Because you can create a compiler without using the word meta model, of course. The meta model is implicitly there. You can't create a compiler without using a meta model, but you don't have to formally call it a meta model. You can just create a set of classes, whatever, that do the job of the abstraction that we described. But the idea here is that by creating this as a first-class citizen, we start to think in terms of these concepts. It's a bit like saying you don't necessarily need to create the concept of an object. You don't have to have the word class in a language. For any of us who programmed in C, we seen how you could create object-oriented code in C without having class language level support for object related concepts. Many of us created, how should I put this, informal processes or informal decisions that will enable you to think of the code as if it was object-oriented. So as an example, you would declare, say, a class called deal, for example. Say inside of the financial domain, you create a class called a class. I use the words in quotes. A class called deal. Now, the way you encode this class is by creating a file called deal.age, in which you define the struct for deal, where you put all the properties of a deal. And then you'd also say, informally in your team, that anything to do with algorithms that are operating in deal must exist on the deal.h file and the deal.c file. And they must all start with deal underscore something. So for example, deal.getBook, for example. This will be your getter for the property book, book ID, for example. And so you'd encode the notion of object orientation in C. And many people took this to the next level. If you look at, say, GTK, or if you look at a lot of the GNOME code that's written in C, it uses object orientation. Now you'd say, well, C is not an object-oriented language, but there's millions of lines of code that are written in C that are object-oriented. The problem is, because C does not support as a first-class concept, the object-oriented concepts, you have an impedance mismatch. You spend a lot of time trying to bend the language to do your bidding, and you also require a lot of training for regular procedural C developers to understand that there is a different way of doing things, and that's the problem when the concept is not actually baked into the language. So the model-driven engineering people are trying to say, actually, it's not just that we need to model, and it's not just that we need to have transforms. We need to make sure that all of this is encoded on the language itself, such that we think in terms of those concepts, and the impedance mismatch is smoothed out. So, in terms of transformations, you could of course create a very simple class with a method that does a transform, and you call it transform, just like you would with C, and that would be a valid way of creating a transformation. But if you had a meta model that defines your transform language, and if you had a specific DSL that talks about transforms, then you would have a much better way of describing what it is that you're trying to do at the right level of abstraction. Just like having the class keyword in C, in C++, and in C Sharp, allows you to think in terms of object orientation without having to deal with natural language and conventions. And if you did things properly, you would then be able to move between meta models via this language of transformations. So the formalization of the meta model, as well as the formalization of the meta models for the meta model for the models, as well as the meta model for the transforms, will enable you to start operating at a very high level of abstraction. Then, of course, the question you're going to ask if you are new to this is, well, if there's a notion of a meta model, isn't there a notion of a meta-meta model? Yeah, of course there is. If you're going to define a meta model, presumably you need some kind of language to define the meta model, and that language is DSL, and as such that DSL has to be representable as a first-class citizen, and so of course you could create a UML diagram for that language, and that is called a meta-meta model. The meta-meta model is there to give you the language that you need to create the model, the meta model, sorry. And as you can see by my confusion there, this is what starts to happen as you start moving up in the abstraction ladder. In the case of UML, we have MOF, which is a meta model that's used in UML. And the idea with the meta model is that you can imagine a family of meta models that are all created using the same meta model. And if you really done your job properly, what that would mean is that you could transform from one meta model to another meta model quite easily, because they're all created using the same meta model. This commonality is it's sort of having a lingua franca between meta models is the thing that will then empower you to move smoothly between different kinds of meta models. But then of course you're then going to say, as Feynman did, I mean, is this turtles all the way? And actually no, once you get to the meta model, you don't really need to keep going up, because there is no huge advantage. You're not talking about such an abstract concept that there is no much of a point to move further up from meta models. And so what people tend to do is they tend to create a sort of a reflexivity or a closure that allows your meta model to be created in terms of the meta model. And then at that point you don't really need to go any further up. So in terms of model-driven engineering, we really only consider three levels or three layers really: the meta model, the meta model, the model, and with that you should be able to represent pretty much everything. And it's worthwhile having a quick look at this diagram. So this was obtained in Wikipedia. So it's a bit difficult sometimes to talk about these concepts without an example. So let's just look at this example that we stole from Wikipedia. So at the object level, we have sort of at the M0 level, we have objects. Objects are the world we're quite familiar with. I mean, every time you knew something, you create an object. So the object is the constructs that programmers are creating all the time at runtime. So we're all quite knowledgeable about that. What we tend to also be very familiar with is classes. So the idea is that when you create an object, you're creating an instance of something. It may appear very obvious to us now that an object is an instance of something, but you have to keep in mind that somebody had to come up with this idea. Because if you come from the, say, the machine code or assembler sort of world, you would just allocate memory. You would just go somewhere in RAM, and you would start to say, okay, this bit here is going to represent, I don't know, XYZ. And it is not entirely trivial to make this leap between the notion that objects in memory all follow a certain pattern, and because of that there is a higher level concept of a class. It's just that because we grew up with this concept, for us we tend to think of it as completely obvious that objects are instances of classes. But if you try to bring yourself back to the 40s and to the days where all of these things were being decided, it is not entirely obvious that such a relationship exists. It required somebody to do the abstraction of the idea of an object into the idea of a class. But we kind of stopped there, really. We got to the class as software engineers, not as computer scientists. We kind of got to the class, and then after that, we more or less said, well, there's really not a lot of need to go past the class, because once you've got a class, we kind of get the gist of it. We know what you mean, and at best, you need the reflection, which enables you to iterate to the existing classes in the system and so on at runtime. But that's kind of it. But once you enter this world of model-driven engineering, we keep going upwards and upwards. So we start to think, well, actually, all these things we create in programs, they also are grouped by types, aren't they? So we create things like classes, we create things like the relationship between classes, we add properties to a class, so there's a thing called an attribute, and so on, right? And so as you're going up in this level of abstraction, you enter M2. And this world you're familiar with if you created a UML diagram, because that's kind of where you are in UML. And then, of course, we enter the meta model lands. And in the meta model lands, we start to think of, actually, attributes, classes, and instances. These are all instances of something, right? And in the moth land, they decided to call that a class. But this class is not the same as this class. This is sort of a meta class, really. It represents the notion that things get classified. And you can see how these things start to get sort of, how these things start to join together to form a hierarchy of modeling. This is also very confusing, I think, for a software engineer, because we can't really see the point of doing all these layers of abstraction. So it's only really when you start to actually use these things in practice that they start to make sense. So I'm not really going to spend a lot of time covering that on this first lecture, because, like I said, this is just an overview to give you an idea, and we already are getting close to an hour. Let's see, I think we still got quite a few slides. Right, so I think we might have to stop here. I think what I'll do is we'll have a two-part overview, because I don't really want to make this too big. So I think what we'll do is we'll do a quick recap then of what we spoke about today, because we only have another 8 minutes. It's just not enough to finish the remaining slides. So we gave you an historical context of what happened in computer science, really. In fact, even the notion of computer science emerged from the work that was being done from in the beginning. So we started off in this revisionist history of ours, which does not correspond to how actually things happened, but in this revisionary history of ours, you start off with people like Ada Lovelace and Babbage, which had a very mathematical view of what a computer is. Ada, completely mathematical, Babbage, mechanical mathematical view. And they imagined that a computer was literally a manipulator of symbols. And they could not see beyond computers and maths. These two things were very, very interconnected. Then you move over to the world of the 40s, where the engineering side took over, and it was much more about getting things done. So in that world, it was much more about plug boards and switches and connecting things together by hand. And at some point, somebody abstracted the notion of the plug board, which is a physical thing, should be designed in software, at which point you start to think of machine code as a way to represent how connectivity is happening in the plug board. And the natural thing is to say connected, not connected. So of course the first representation of machine code is going to be some kind of binary form. Then the next level from there is somebody will eventually say, well, it's a pain in the backside to have to deal with all these ones and zeros, so can we not just have an hexadecimal representation of that? That's actually a very, very straightforward mapping between hexadecimal and binary. It's almost the same thing, just much easier for a human to remember, say, 0xFF than it is to represent 1111111 and so on. And that clearly is very helpful, because you imagine how much you're condensing information there. Then the next logical step is for somebody to say, well, actually, I'm not going to be able to remember all these hexadecimal numbers. I mean, not everybody is, able to remember very large sequences of hexadecimal numbers. So can we just do something that's slightly more connected to the way the neocortex works? And the neocortex works in terms of the words and sentences and so on. So the logical conclusion was to create assembler, because assembler is, again, just like hexadecimal to binary, is a very straightforward mapping between machine code and assembler. You could just basically say, well, this 0FF, 0xFF maps to instruction, I don't know, L loads, for instance, and so every time I type load, just convert that into 0xFF. And so whilst this may appear to be very trivial in terms of abstraction, this is actually a leap, a conceptual leap, because the number of people, whilst we're talking about very small sets of people, you can imagine this as a sort of a ring of sets that keep on expanding. The number of people that are able to work with plugboards is very, very limited. The number of people that were able to work in binary is very, very limited, but it's perhaps slightly wider than the number of people that work with plugboards. The number of people that can work in hexadecimal is again a bit wider than the number of people that can work in binary. And the number of people that can work in assembler is much, much, much broader than the number of people that can work in hexadecimal. And so what's happening here is as we increase the level of abstraction, we get closer and closer to our normal or average people work, which makes computing more accessible. And so the next logical step, which is, if you think of it in terms of magnitude, between plugboards to binary, we did a bit of a step, and then from binary to hexadecimal, we did a bit of a step again, but not huge. Then from binary to assembler, it's a very large step, because now you're talking about something that's much closer to how the brain works. And then from binary to, say, the first high-level languages such as Fortran and Lisp, it is a step of many orders of magnitude. It's not just it's not just a small quantitative step. It's a qualitative step. The fundamental notion of what it is to program a machine was completely changed by this step. And the number of people that are able to do programming is many orders of magnitude bigger than the number of people that can do plugboards, because we now no longer need to concern ourselves with the physics and electronics. We are now able to abstract all those notions away, and now I can instantiate the class without having to understand how an electron propagates over a cable. And then the idea of MDE is to think of this as a timeline, and to think what is happening in this continuum. What is the next logical step? Given that we are abstracting and abstracting and abstracting, what is the logical end game of this abstraction? And what they propose then is, after the design of high-level languages, and of course, as you can imagine, the higher-level languages became higher and higher. So, for instance, from, say, Fortran to C to C, to, say, Visual Basic, there is an increasing of the abstraction level. A person using Visual Basic or Smalltalk is able to think at a much higher level of abstraction, mainly because of the class library. The class library is the thing that enables you to now say, I don't really need to worry about copying strings, for example. I don't need to allocate memory to copy a couple of strings. I'm not sure if you need to do this in Fortran, because I never coded in Fortran, but I'd imagine C, for example, you still need to worry about strings. There's a problem there, because you want to worry about the domain, the thing you're actually coding for, not about concatenating strings or allocating strings and so on. So Visual Basic and Smalltalk, and these are the languages, and even C# now, their platform, the set of concepts that come bundled in with the language, is very, very big, which then in turn enables you to think very abstractly about the thing you're trying to code. But that is sort of a linear direction of where we're going. Model-driven engineering is proposing that we kind of do another qualitative step in terms of this abstraction process. Not just increase your class library, but rethink what we mean by programming altogether, which is kind of what we did when we moved from assembler to high-level languages. And that's why it is very difficult to get your head around model-driven engineering, because it's such a rethink. I'm just going to go back to the first topic, just to first slide. We are rethinking the general idea what it means to do programming. So I think we'll stop here, because I think there's a lot of concepts being introduced. Like I say, if you have any questions, please just leave that on the YouTube comments. I will pick up the questions as they come in. And in the next video, we will look into, we'll continue this overview because I think it's important just to give an overview of what you're trying to achieve. And we will talk about the two key concepts that we discussed today, platforms and technical spaces, because these are very important. So hopefully that made sense, and I shall see you in the next session. Thanks for watching.